So in the last chapter, we studied kinematics, which was the motion of objects with position, velocity, and acceleration. In this chapter, we're going to then look at dynamics, which is how objects move. So we're going to talk about forces in motion. This begins all the way back almost 2,000 years ago with Aristotle, a little over 2,000 years, in the 3 to 400 BC. So remember, he was a Greek philosopher. He also studied science. And so when he looked at and observed the things around him, he believed that everything wanted to return to its own. So if he picked a rock up from the ground and let go of it, that rock would fall back to the earth. As he looked at his campfire and saw the smoke rising up, the smoke was made of part of those air particles. And so he saw that that smoke wanted to go up into the air where the rest of the air was. And he made this observation that said, hey, objects really want to be in a state of rest. So when I drop the rock, it hits the earth and it stays there. It doesn't move at all. Whenever the smoke comes up into the air, it stays up in that air and just kind of rests in the layer that it becomes. And whenever you sort of remove all of our scientific knowledge right now and just think Aristotle was just trying to describe and observe the world around him, a lot of it sort of makes sense with what happened. So skip ahead 2,000 years because his ideology sort of had a stranglehold on science and philosophy for that long. And along comes Galileo. Galileo in the 1600s, he's in this quest to figure out more about gravity. So he starts taking these objects and dropping them from the Leaning Tower of Pisa. So based on the kinematics that we studied in the last chapter, it takes about 3 seconds for the object to fall from the top of the Leaning Tower of Pisa. Once it gets to the ground, it's traveling almost 29 meters per second, which is about 64 miles an hour. And it will be traveling at about a half of a football field every second. Now, think through in Galileo's age, that's going to be really difficult for him to measure. And so what he does is he slows things down by rolling these balls down different inclines. And he takes and sets up this incline here so that it comes down one side, rolls up another side, and lo and behold, he finds that the ball comes up to just about exactly the same height that it started from. So he said, well, that's really interesting. So he makes another hill that comes up this shallower angle, and he finds that when he does that, the ball comes up to almost exactly the same height again. So it does a shallower angle, it comes up to about the same height. And Galileo gets to the point where he says, well, what if I never make the right side of this incline? What if it never gets back to that same height again? And he comes up with this amazing statement that says, hey, if that surface goes on forever, then wouldn't that object want to keep rolling forever because it's never going to get back to the same height? Now, think through, we're ignoring air friction, we're ignoring friction between the tracks. So these balls didn't actually come quite to the same height. They came a little bit lower because of that, but Galileo sort of put that idea into there. And so he comes up with this idea of inertia, and he says, hey, there's a tendency of an object to want to stay at rest or to stay in motion. So notice there's part of what Aristotle said there, but there's this whole other key idea that if it's in motion, it wants to keep or stay in motion. So Newton comes along. He was a young man whenever Galileo was an old man. He takes these ideas from Galileo and he sort of meshes it together and he says, oh, okay, so an object wants to stay at rest or it wants to stay in motion based on its inertia. Well, how do we measure inertia? And he comes along and says, it's got to be the mass of the object. It's got to be the mass. So the more massive an object is, the less it wants to change its motion, which should be kind of easy to think through. If I put a kickball on the ground and I put a bowling ball on the ground and I say, I want you to kick both of them to get them to change their motion, which one are you going to want to kick? You're obviously going to want to kick the kickball because it will be easier to change its motion from that, and it will hurt your foot a whole lot less. Or if I put you out on the road and I say, hey, my daughter is riding her tricycle towards you going 10 miles an hour, or there's a semi coming at you going 10 miles an hour, which one do you have the greater chance of changing its motion? You hopefully are going to say my daughter on the tricycle because she has less mass, so it'll be easier for you to change that. So the more mass you have, the less you want to change your state of motion, whether you're sitting still or whether you are moving. And that's really the crux of Newton's first law then, that an object in motion stays in motion with a constant velocity, and an object at rest stays at rest unless acted on by an unbalanced force or an outside force. So without anything else acting on them, they either want to stay in motion or they want to stay sitting still. And then if they are changing that, that's where that unbalanced force comes in. So we probably need to talk about, well, what really is a force? A force is a push or a pull on an object. We measure it now in newtons. We named it the unit after Sir Isaac Newton in honor of the stuff that the experiments that he did with this and the discoveries that he made. Obviously, he didn't measure it in newtons at that time. And the net force, then, a key thing that you have to know is that the net is the sum of all of the forces, the sum. Anytime we talk net, we're talking sum. If we talk net charge, it's the sum of all the charges. If we talk net momentum, it's the sum of all the momentums. Net force is the sum of all of the forces acting on the object. So balanced and unbalanced. A balanced force will be if I have this object here, maybe it is a shopping cart. You're pushing on a shopping cart with 2 newtons towards the right, and you have a friend who is pushing on the shopping cart with 2 newtons towards the left. Notice the negative tells you the direction there. So if I have the net force, 2 plus a negative 2, and instinctively you should know that nothing is going to happen to that shopping cart because it all cancels out. In an unbalanced force, maybe your friend has been working out and has gotten really buff, and you are still pushing on it with 2 newtons, and they become very persuasive and says, no, I want to go back to the gummy bear aisle and get gummy bears. So they push on you with negative 5. Then notice that your net force, or the sum of all of the forces, is going to be 2 plus the negative 5, which gives you a negative 3. Now, that also tells you, remember that negative will tell you the direction that the net force is in. So your net force is going to be pushing towards the left with a 3 Newton magnitude. So force diagrams, one of the best ways for us to start describing problems in the dynamics chapter is to draw a picture that has all of the forces acting on it. Sometimes this is called a free body diagram, but all that it means is it's a vector diagram of all of the forces acting on the object. So here you are, you're moving into college, you're dragging this box across your dorm floor, trying to move in. So the first thing we would do is we would draw the object as a single dot. So I'm going to condense this whole box down to its center of mass and say right at that point, all of the forces acting on it are acting on it at that point. Number 2, draw the forces as vectors coming out of the dot and then label each of the vectors. So I might say, hey, there is the force of U pulling out. I'm going to say the force F with the subscript of U. A lot of times you will see physicists will abbreviate these forces into a single letter instead of doing F with the subscript. That's okay too, as long as you understand what each of those letters represent. I might also look at this box and say, hey, what else is acting on it? Well, there has to be gravity. Gravity is always pulling an object down. So I'm going to pull this and say F sub G for gravity. If you single letter that, normally you would see that as a W for weight. And then I might say, oh, that's all the forces acting on it. There's nothing else acting on it. But that's probably not true. Check to make sure that all of your forces are accounted for. And there are 2 types of forces that you want to look at. The first is contact forces. Any forces, any of the 2 objects that are touching it, they are contacts. Like, for instance, you pulling on this is a contact force. Now I'd look at it and say, well, isn't this box isn't floating or sinking, so there has to be some force of the ground acting on it. And if I'm dragging it across the ground, isn't there going to be some kind of friction? So when friction is on it, remember that friction is always acting against the direction of the motion. So I'm going to draw an arrow against it and say that that's the force of friction. If you're going to use a single letter, kind of like we did the W down here, then sometimes you'll see that as a cursive F would be your single letter for that. But then there's one more thing that we would look at it. Before we do that, so the second type of force is the non-contact force, and that would be gravity, electricity, magnetism, anything that doesn't have to be touching the object in order to do it. Interestingly enough, we believe that there is no such thing as a contact force, that it's really the electrons and protons that are repelling and pushing on objects that create that contact, but that's a story for another time. So when we look at this, I would say there are a couple different things here. Well, the box isn't floating or sinking, so there also has to be another force. Not only is the ground creating this frictional force that's the drag force, but I would also say that the ground is pushing up on the object that we're going to call the normal force. So F sub m. And if you write that as a single letter one, often you'll see it as sort of an uppercase N. For that. And that normal force is the force that's perpendicular to the ground pushing up. So what's key to that is this word normal doesn't mean not weird. It means, it's the math term that means perpendicular. So the normal force always has to be perpendicular to the ground. The ground can never push up on you any other way than perpendicular from itself. And so whenever I look at this, then I would look at that and say that is probably a more complete force diagram, because part of the U component and the normal force will cancel out with gravity, and then part of the U component and the friction force will cancel out but give you the force that's pulling you forward in that direction. And so that gives you an idea sort of what Newton's first law is, and it also gives you the beginning of how to draw some of the force diagrams that you're going to do in this particular chapter.